Yes, thank you very much, Juliet. So I will give a short introduction on our work package, and then later Jim will proceed and Silesh with some more detailed presentations. So our work package sediment handling is within the future hydropower plants work package from that is led from Jonas Bergmann-Paulsen. And the question that was asked was like, what is the ideal hydropower plant in the future? And it's, of course, a sustainable one. So we would like to use the natural resources in a way that we also support future generations. So I have here a very simplified picture from the sediment cycle. So we have the sediments that go from the mountains to the sea, and then the new sediments will be produced, and then it should be a cycle. And even more simplified site perspective of a river and sediments and river ecosystem and how it will flow downstream. So if we build hydraulic structures, then we will interrupt this system. And if we build several, then even more. And these hydraulic structures, these hydropower plants can have a very different setup, as we all here know. So the upstream and the downstream effects of the hydraulic structures, they depend a lot on the plant itself, so what kind of hydropower plant it is, but also a lot on the environmental system and the river system. So what is locally happening? How is the hydropower plant run? How is the operation? And then also how is the sediment management strategy of the plant? So the World Bank said last century was used to build hydropower reservoirs, and this one will be used to solve sediment problems. So that's where our work package is working on, and we work on several topics related to that. And it's there's always this I think most of you should know the different management strategies. So we can either reduce the sediment yield from upstream, have check dams, or slope protection, for example, so that we get less sediments into the hydropower system. Then we can also remove them through dredging, for example, or with sand traps, exclude them. We can route them around or route them through the hydropower plant or bypass them. And we can also have adaptive strategies so that we change the dam height, for example, or we change the turbines. So what we want is the most sustainable solution, of course. So what is very favorite is getting the sediment through and like getting as close as possible to a natural situation back. And there are several ways how we can do that. So it's not just through sediment routing. And of course, what we also need, we need economically sound solutions. And that should not be just from the business perspective. It should also be from the macroeconomic perspective that this is useful. So today, Jim will start to present, to give an overview of what has been done already and what is planned on the economic effect. And then also what we will combine in this work package are the structural measures and also the turbine measures. And in addition, we will evaluate the environmental consequences. So what is needed for that is that we also have insights in the turbine and the structural measures. So that will be the second part that will where Silesh will present. And that will be on the work from Kathmandu University and how their turbine design can be improved for extreme sediment conditions. And then, as Juliet said, it's like the first presentation today from a series of sediment presentations. So we will have a couple of more lunch presentations on sediments. And we also work on sand traps together with Kathmandu University to also compare. Jim will also show some details on that. We work on the routing and bypassing of sediments, so sediment bypass tunnels, for example, but also how the sediments flow in the hydropower tunnels themselves. And we work on the river ecosystem itself. And yeah, we have a lot of project partners for that. And we have till now 3 test cases, but we will have some more, but these are the ones we have worked on so far. And here are the names from the partners from the project. So yes, then Jim would be the next to present. Thank you.
All right. Thank you very much, Elena, for the introduction. And I will try to give a little more of details about the project. In this case, the sediment handling. As we can see in this slide, this is the normal hydropower plant. We have the dam, the equipment, the waterways, and everything as usual happens in the hydropower plant. And this is like the life cycles of one normal hydropower plant. So we have expenses in the hydropower plant, the general OPEX in the hydropower plant, like the operational expenses, operational. We have at the beginning some part of like a frequently short because when the hydropower plant is built, we have the fresh failures. And then we have a more regular expenses, and then increase a little bit after some years because we have the life cycles, for example, of the electronic equipment needs to be replaced after 10 years or 12 years. And then these expenses of the hydropower plant decrease more in the time when it's like the life cycle completely because you need to decrease the life of the hydropower plant expenses before you shut down. This is when you analyze just directly the life of hydropower plant. This is one example of one turbine here in Ulsan hydropower plant. We have outside the laboratory. This is after almost 4 years of working. So as you can see, the turbine is normal, as you retired for improvement. And same with this example of a blue shore reservoir in Sultan. You can, I wish to point it. Yeah, we see here this is the limit of the border of the dam, and we don't have any sedimentation here, so it's a normal cycle of hydropower plant without any issues about lost volume. And when we analyze this with hydropower but with sediments, we deal first with loss of storage capacity because all the sediments start to trap in the dams and create the loss of capacity. And that leads to dam maintenance. So we need to do maintenance of the dam. So try to recover the capacity that was planned at the beginning, or at least some part. Also is the sediment erosion on the turbines. The turbines has these effects. All the sediments create this effect like a sandblast and destroy the surface of the turbine and also create some effects. Loss of materials and cavitation effects, and we need to introduce turbine maintenance because we need to recover the original geometries, not only for the sake of the turbine, also for the loss of efficiency because we are losing water, with less efficiency. Before was this example of flushing dams because was another way to recover some capacity. Just open the gates in the bottom part of the dam and flushing. This is more or less the structure. You see here, we have bottom outlets in the dams, and you can open and flush the sediments. But it's to recover only some part. It's not completely recover all the capacity. Here we have some videos about that. For example, this is in Yellow River in China. As you can see, the color of the flash is a little different for the color of the other water. Because the concentration of sediments. Also, this is in Salam Dam in India. You will see the same. The bottom part of the water has more sediment concentration compared to the upper layer, and that's why you have all the flushing of the sediments. But okay, as we see now, it's easy to figure it out. Like we have problems with the life over the fish of the environmental on the river and impact. No? This is a problem that was growing. For example, this is the flashing dam regulation timeline in Switzerland. As you can see, before 17 was no regulations at all, so you can open as much as you want. In 17.1, they create this flashing timing switching to have more regulation about the timing, when it's optimal to open the gates. But still was they found some problems. After 91, they regulated 10 millimeters per liter strictly, but this creates some problem after 2012 because most of the dam was filled and without properly safety. So after 2012, they have this 5 grams per liter, 10 grams per liter maximum 6 hours, and 15 in the 30 minutes. So this regulation is all the time more strict. So also is growing in different places. If we see now around the world, for example, France has the same regulation as Switzerland. Italy has like a less than 4 grams. Spain, when in this case in Spain and Norway, we don't have too much sediment. So that's why there is no strict regulation about how to clean the dams. But they have some focus in a specific, according to a specific dam. In Nepal, the regulation is 20 grams per liter. In China is 110 and 200 grams per liter. So that is very far compared for Switzerland, but we expect like this is going to decrease in the time, like was the timeline of Switzerland. And India has some regulations, and Taiwan is coordinated according to typhoons. So, and in South America is case by case in each power plant. Flashing is not an option, so we need to deal with decreasing the option. We need to deal with problems of the impacts of the hydropower plants, in this case, in the river biodiversity and the agriculture, because we keep some of the sand with minerals to the useful for the agriculture. So we have a reduce of the share, hydro peaking. Also, we alter the thermal regimen of the river. How impact this in the economic life of the hydropower plant? We can see here, for example, this was the normal hydropower plant expenses. This is how it's later, because we have more turbine maintenance, we have a new runner after sometimes, dam maintenance, and so this increase the expenses of the hydropower plant. And also we have the river biodiversity risk market. Why? Because this is difficult to measure. It's not like we have a taxes to pay, and this is the tax according how is according how we impact in the river. But we have the other way. We have the risk in the market, because most of the hydropower plants are in the market, in the stock market. So that means the reputation is important. If we have some problems with river biodiversity agriculture, it's going to affect the risk market for us. So in total, it's going to increase the expenses of the hydropower plant in the all the alternatives. So that's why we have this. What is exactly the strategies that we have? Was also explained by Elena. We have, for example, the option of the sediment bypass tunnel, that we can bypass the sediments. Also, the sand trams could be increased and handling more the sediments, and also improve the design of the turbines and operations, so that turbines can handle more sediments, and we can pass the sediment to the turbines. And the final is improve the sediment quality to the downriver. All these strategies is going to be evaluated and measured according to the timeline of the hydropower plant. We have these 4 pillars for the project. One is the sediment bypass tunnel, the sand traps, improve the sediment quality, and improve the turbine design. We have like a combined assessment and case studies also, and everything will be integrated to the economic and environmental decision support for the model, and looking in the completely timeline of the hydropower plant, including the capex, the investment in the constructions, all the operations, no? The expenses and the maintenance of security and costs related to the rigs also. That is for my part. More or less, this is the overview of the economic life of the hydropower plant. Now I will give pass to Silas from the Kathmandu University, who is working specific more in the turbines, as Elena mentioned as well.
Thank you very much, Jim. Jim pictured the holistic aspect of the project, where I'll be shifting a little bit towards the mechanical aspect and look into what works have been done in the hydropower turbines, especially in terms of sediment erosion, and what we will be doing, particularly in this project, RenewHydro, from our side. Just give a little small picture about the status of hydropower development in Nepal, since many of us might not understand the thing. So I'm just giving you a small picture. These are the recent data of the hydropower development. We have now successfully installed 3,600, more than 3,600 megawatt capacity in Nepal. But if you look at the planned projects, more than 36,000 megawatts of capacity are still in the developing phase. They are in different stages of development. But Nepal is also prone to these types of disasters now and then. So these are the pictures from the flood from last year and also from this year, which affected several hydropower plants. Although Nepal is blessed with a lot of hydropower potential, we have fairly young tectonics, and because of all the geographic and climatic regions, the issues related to flood, landslides, and extreme sedimentation is very common here. And apart from that, this is the map of suspended sediment yield, which shows that 70% of the 7 billion tons of the suspended sediments that are carried into the ocean are contributed from Southern Asia in the Pacific and Indian Oceans. And out of this, 0.6 billion tons of sediment is coming from Nepal only. So this is fascinating because we can imagine the amount of problems that it can bring to hydropower plants here. For mechanical engineers like us, the challenges related to sediment erosion in hydropower turbines remains inevitable. All of these turbines are of Nepalese hydropower plants. Erosion has actually plenty of after effects, and one problem is usually the source of another problem. So in any case, there is an additional financial burden to the power plant in order to tackle different problems. I'm just quickly going to show you how what is the timeline of the sediment erosion study at KU. So it started in early 2000 when our one of the professors, Professor Bola Thapa, did his PhD in the sand erosion in hydraulic turbines, where he studied that more than 50% of the sediment constitutes in the sand in Nepal is quartz. So it is one of the hardest minerals. Then we had some numerical simulations of Francis turbines especially. Then we built some erosion modeling in previous studies, and we did some optimization of those turbines. And proposed a better design, and also did some experimental validations using some simplified setups at the in the beginning. Then my PhD was more related to guide vane erosion and how we can mitigate the erosion in the guide vanes and runners by changing the guide vane profiles. So there were a lot of studies related to experiments and also related to CFDs. We continued with the different masters and PhD programs. Later on, conducted several experiments on the optimization of the guide vanes and also runner blades, and also verified that with experiments. Later on, we also built experimental setup where we could test our optimization strategies and results. So later on, we also moved to labyrinth seals of turbines and also did quite many simulations and experiments. We also then optimized one hydropower turbine, Francis turbine, for runner to mitigate, or let's say improve, the impact of the sediments, and it was also later on tested in the power plant. So a lot of studies have been going on in terms of the sediment erosion here at KU and turbine testing lab. And later on we also, as I said earlier, we plan to also prove, or let's say provide the services to the hydropower companies, real hydropower companies. So this was the runner which was initially very much eroded. Then we did actually, Amul was one of the researchers in this project, where he designed the completely new runner set for the power plant, maintaining the main dimensions. And I got this result just last week from the power plant. This ran for one monsoon season, and we could see that the new runner is showing minimum impact of sediments on their runner blades. So that was one kind of verifications to our optimization works, and it worked very well. So we are trying to bridge also the gap between industries and academia here at KU. So this is the turbine lab, if you have not been there. So it is newly built. It was established in 2011, but the other components were added on year by year and component by component. But the thing is that the lab is not able to perform experiments by including sediments, because then we would destroy our machine. So this is only for hydraulic testing of the turbines and conduct some other sophisticated measurements. But we also have a separate rig, sediment erosion rig facility available, which we think that we'll be using a lot in this project. In this rig, we inject the sediments into the turbines, and also we do the measurements of the erosion on the turbine components. And we have used this for several master's and PhD studies before as well. Especially we use it for validating our CFD results. So CFD, we get the results, but we need to make sure that the results are making sense. So in order to do that, we have come up with some of the unique experimental strategies. For example, by coating the components with different colors, so as to match the experimental, or let's say match the experimental results with the numerical results. And we have got quite a good results so far in the guide vanes, and as well as for the runners. And we have come up with some of the theories, or let's say some of the flow behaviors that matches with our hypothesis, and we can clarify that, okay, there are some flow phenomena that is occurring inside the turbines. So for these kind of activities, we are using this experimental setup. You can also see CFD results is matching quite well with the experimental results. So different students, they build this setup based on their own requirements, and they do testing, and it is taken out again. And we use it for another testing. So this is for Francis runner blades, where we can see that numerical results are matching quite well with the experimental results. Before this rig, it was really difficult for us to validate our numerical results, but this experiment is actually experimental setup is actually helping us a lot in order to do these kind of testing works for validation purposes. And regarding the RenewHydro project, I think Elena and Jim mentioned it a little bit from their perspective. Also from the perspective of the turbines, when we have a desilting basin that usually traps the sediments 90% with a 90% efficiency for particle size greater than 0.2 mm. If we plan to change the design, considering all the economic requirements like CapEx, OpEx that Jim talked about, then what will be the consequence of changing the size of the desilting basin? For example, if we reduce the size of the desilting basin, of course, it will cause less amount of investment cost, but then it will increase the operational cost. But can that operational cost be justified? So that was one concern. In this particular project of RenewHydro, we will have the research question: is it possible to increase the sediment load and size passing through the turbines with improved maintenance or design strategies, so that we can reduce the cost of hydraulic structure? So that is the research question. So the planned activities for this project is first to study the erosion tendency for various sediment characteristics. We have mostly been working for different sediment size. So we will kind of develop a correlation between the sediment size and erosion for our requirements for the turbines. And then the mineral contents, concentration, shape. So these are some of the sediment characteristics that we plan to study. And we have also been looking into developing a separate erosion rig, a very simplified setup compared to the one we have, so that we can go deep into the fundamentals of the erosion and develop these kind of the correlations and some mathematical models between the sediment characteristics, flow components, as well as erosion. So some of the erosion rig has been conceptualized now, and it is in the process of development. And then the second part would be to design the turbine for extreme sediment conditions. So again, going back to our original studies where we optimized the design of the turbines, so we will be using that in order to redesign or rethink the design strategies of the turbines to handle these extreme conditions. Extreme in the sense that there will be more sediment concentrations, larger sediment size. So we'll be looking from these perspectives for our future studies. So we will be strengthening our numerical model, especially CFD model, and we will be introducing a deformation model as well. So we are thinking of creating this kind of the multi-physics environment between CFD and the structure, and use the deformation model and validate that the model with our experimental results, so that we can validate our optimization strategies as well. So these are some of the planned activities for this project. So with that, I think I end my slide. Thank you very much.